Hello, my name is Emmett Boyle and I am the president of the Michigan Mars Rover team. Rover is a student-run robotics team with about 45 members. This past year, the team strove to create a rover that will ensure Rover is a top competitor at the 2018 University Rover Challenge. We are now pleased to showcase this year's design.
This year's rover introduces an all-new mobility system. The system features 4 wheels with reinforced in-hub motors, polyurethane treads, and custom spring dampers, all mounted on 2 rockers. Our dampers have been specifically designed and fabricated in-house, providing the necessary shock absorption to keep other rover systems isolated from the worst loads. Additionally, the passively pivoting rockers are connected with the differential bar, allowing for near constant ground contact and even weight distribution across the wheels while keeping the chassis stable. The 4 competition tasks each require a different configuration of the rover, necessitating a modular and accessible design to allow for quick setup and teardown. We have met these requirements by implementing a lightweight carbon fiber design that forms a 3x3 grid of squares for mounting all of our external systems. The objectives presented in the extreme retrieval and delivery task and equipment servicing task require a robotic arm with high reach and dexterity. To meet these requirements, we've designed a 6 degree of freedom robotic arm with a 35-inch reach mounted at the front of our chassis with the flexibility to reach in front and below the rover with our end effector. The end effector uses 4 fingers with silicone gripping surfaces. At the furthest extension of the fingers, a probe extends to press keyboard buttons and perform other high-precision operations. From previous competition experience, we know that the hard, clay-like soil that we are tasked to collect and test is difficult to retrieve. This is why we've revamped our soil acquisition system with a more powerful drill enhanced with a rotary percussion action. The rate and force of percussive strikes can be adjusted during operation to quickly adapt to soil conditions. This augmented mechanism will allow the system to break through the ground and collect soil from up to 15 centimeters below the surface. Once collected, internal doors shut to temporarily house the sample before the operator deposits them in our cache containers for further testing on board and off board the rover.
Using satellite imagery, we've analyzed the competition site to look for distinct geological features such as dried riverbeds and loamy soil. Onboard analyses include soil moisture, pH, conductivity, and temperature tests. The results of these tests indicate the presence of key ingredients for sustainable life. Off-board tests include a BCA assay and Sudan-4 dye to search for specific biomolecules that can provide proof of life and validate our site selection.
The electrical hardware is split into 2 custom electrical boxes. The Logic box houses the Jetson TX2, the Raspberry Pi Zeros, and our custom PCBs. These systems control the rover as well as collecting visual, scientific, and telemetry data. The power box contains 10 motor controllers and our power distribution system. The rover's LiPo battery is external to these electrical boxes. The team is printing its own custom PCBs to handle science data as well as data from sensors used for autonomy. These PCBs allow us to save space that would be taken up by more traditional microprocessors.
Our hardware interface handles communication between our onboard computer and hardware peripherals. It makes heavy use of the CAN bus to communicate between our onboard computer, motor controllers, and our microcontroller boards. Our boards are designed to interface with science and odometry sensors using a CAN protocol, allowing for very low latency when handling controls and sensor data.
The teleoperated system communicates between the base station and the onboard computer. This year, the teleoperated system is designed with a focus on usability. We have developed an efficient graphical user interface based on our experience at past URCs. It provides a map of the competition site with the rover's current location and allows the operator to enter GPS waypoints to track the rover's progress in each task.
For radio communications, we have chosen to use the 900 MHz ISM band. This band is able to penetrate objects more effectively than other ISM options. Our operators are ham radio licensed, which enables us to use an amplifier to extend the range of our 900 MHz radio.
The autonomous system reads from a perceptual sensor array and determines how to traverse a course of GPS waypoints. Our autonomy stack uses a layer design for ease of code maintainability. At the most basic level of abstraction, layer 1, we read odometry data from our RTK GPS unit and 9-axis IMU to direct the rover toward a target waypoint. Layer 2 adds the ability to traverse a course consisting of multiple waypoints and methodically search around particular waypoints for a tennis ball. Our highest level of abstraction is our perception system, which detects tennis balls using a color-augmented circle detector and analyzes contours from the stereoscopic camera to detect obstacles.
Our team has manufactured and assembled the critical systems of the rover and achieved basic functionality. We are on track to be competition ready well before June. We will continue to test and tune our rover during the months leading up to competition using environments we have designed to simulate the various competition tasks. We will be prepared for anything the URC throws at us. On behalf of the Michigan Mars Rover team, we thank you for your consideration and go blue.